Alright, welcome back. So we're still talking about atoms, and now we're going to start talking about molecules that atoms form. Now in the last quick concept lecture we looked at the structure of the atom and how atoms are grouped into elements and how we therefore determine atomic number and atomic mass. This amount of information allows us then to see how atoms interact with each other and form bonds which create molecules, and molecules create larger molecules, and those larger molecules go on to create cell organelles which eventually form cells. And the cell, is the basic unit of living matter. So starting at the atomic level we can build all the way up to see how a cell is formed, and that is a very important concept in physiology because the structures that actually hold the cell together determine the kind of physiology that can take place inside the cell and between that one cell and another cell. So we're comfortable, hopefully, with the idea that the atom has a nucleus. Inside the nucleus you find positively charged protons, you find neutrally charged neutrons which allow the protons to mass together without forcing each other apart and breaking the atom. Surrounding that we have electrons, and because we are referring to something as an atom, we know that the number of protons in the nucleus and the number of electrons that are orbiting that nucleus are equal, because an atom has no overall charge, therefore protons must equal electrons. Positive must equal negative, therefore zero charge is formed. Now we want to go on and look at the different types of interactions atoms can have that create different types of bonds, and how those bonds form and how strong that they actually are. Now again, we're keeping this simple, so right at the start we're just going to say what bonds we're going to look at. So we're going to look at ionic bonds, which are weak magnetic charges attracting to each other. We're then going to go on and look at covalent bonds, and these are stronger bonds because they share electrons between the two partners. And there's two types of covalent bonding. There is polar and there is non-polar, and we'll explain what those terms mean and why they're different from each other when we get there. And then finally, in the next short talk, we're going to look at the properties of water. And one of the properties, or important properties of water, is that they form another type of bond called the hydrogen bond. Because remember, water is H2O, two hydrogen atoms bonded to an oxygen atom, and that hydrogen and the oxygen can interact with things put into it, and hence they can dissolve in it. And that's an important concept that we'll look at in the next lecture. But for this one, we're going to go back and look at the atom. We're going to understand the electron shells and how the electrons are arranged outside of the nucleus, and that's going to help us understand how they form 1. Ionic bonds, and then 2. Covalent bonds. And that will allow us to understand much more about the macromolecules, things like proteins, etc., and how they form their shape. Alright, so on the diagram behind me I've put some stuff up. Hopefully this is a bit familiar. We've got the nucleus now, so this is the protons and the neutrons sitting inside here. And then we have electrons orbiting on the outside. Now I've put different colours to try and highlight the different shells. Now this is a very simplified version of what's really happening, but we're not going to do chemistry, we're not going on in that sense, so we are just going to accept this as a rudimentary version of what's really happening. So what is this? Well, in the green shell closest to the nucleus is the first shell. It's the first layer of the onion, so to speak. So this shell can only hold 2 electrons. So once it's 2 electrons in it, it's full. So then if you have another electron, a third electron, it has to go outside of the first shell and sit in the second shell. So the second shell is in red, and this shell can hold 8 electrons. So this shell won't get filled up until you've got 2 plus 8 equaling 10 electrons, and that's when it becomes full. The shell outside of that also holds 8 electrons, and this is the third shell from the nucleus, and 2 plus 8 plus 8 is 18 electrons to fill that one up. Now, why do we care about how many electrons are held in a shell? Well, we care because the atom's goal in its existence, if you like, is to become stable and to remain stable. Now, to do that, it needs to fill up its outer shell one way or another, whichever outer shell it happens to have. It tries to fill them up if it doesn't naturally have enough electrons in its outer shell. Now, this is why it forms bonds, both ionic and covalent, to actually fill, in one way or another, the outer shell and become stable. An atom which doesn't have a full outer shell, which is the majority of elements that we have in the universe, these are by themselves unstable and therefore look to make connections to become stable. So, if I drew a very, very simplified periodic table up here. So we've got hydrogen here, there's groups. Now, this is groups 1 to 8. In modern chemistry, there are many more groups than that, but again, we just don't need that level of detail, so we'll keep it simple and keep to the old grouping numbers. So group 1, group 2, 3, 4, all the way through to group 8. Now, group 1 are so grouped because they all have one electron in their outer shell. So for hydrogen, that's just one electron in the first shell because it's got one proton in there and one electron out there. So it's one in the outer shell. So it's the lightest and sits at the top. The one sitting below it, lithium, has 3 protons and 3 electrons. So if we think that one through, we've got the 2 electrons here filling the first shell, and then the third electron is just the one sitting in the second shell, but it's still just got one on the outer shell, so it's still a group 1 element. Sodium. Sodium has 11, so it's got 2 plus 8, 10, and 1 in the third shell. Again, it's just got 1 electron sitting in that outside shell. Potassium, again we take it out another 1, and we end up with 1 in the fourth shell. So the group 1 elements all have 1 electron in their outer shell. Now hopefully you can make an intuitive leap now and say, okay, well group 2 will have 2 in their outer shell. And then group 3 will have 3, 4 will have 4, 5 will have 5, 6 will have 6, and 7 will have 7. And then in this final group over here called the noble gases, sometimes the inert gases, helium, neon, argon, etc., they all have full outer shells. So they're quite unique in the elemental world because these guys are already full. So helium has 2 in its outer shell, so the first shell's full. Neon has 8 in its outer shell and 2 in the first, so 10. It is full, and argon does the same in the third, and krypton, etc. They carry on for each one of the shells. So these elements do not need to interact with anything else. They're already stable, they're completely and utterly solid. So to make one of the group 8 gases interact is extremely difficult chemically. You have to put in huge amounts of force or energy to actually cause the atoms to break apart. So they're stable, but for the rest of them, groups 1 to 7, they have to find another element to try and fill up its outer shell. So there's essentially 2 ways of doing this. The first way is the ionic way. Now, an ion is an atom which has a charge. So we've just got finished saying atoms cannot have an overall charge, and that's absolutely true. A hydrogen atom has no overall charge. It's got 1 proton in the centre and 1 electron around the outside. Equal charge, 1 proton, 1 positive, 1 negative equals no overcharge. However, it can potentially lose its outer electron. In this group 1 here, they all have 1 electron in their outer shell. Now in some cases it's just easier to just shed that electron and give it to an element that needs just 1 electron to fill its outer shell, and oh look, here's group 7, and they're all 7 in their outer shell, here, here and on. Therefore they just need 1 electron to become full. So these guys over here can donate one electron to these guys over here, particularly chloride in biological systems, and they can lose that excess electron, go back to the shell below it and be full, but now have a charge because they've just let go of an electron, so they're now overall positively charged. So for example, a very important biological elements are these two here, sodium and potassium. So sodium is written like that when it's an atom. It has no overall charge. But when it drops off, it's one electron in here, because remember it's 2, 8 and then 1. Once that one has left, we write it like that, sodium with a positive charge, because now it's got one more proton in the centre than it has electrons surrounding it, because it's let that electron go. Now here we have chlorine. Now chlorine just needs one electron. The sodium has just given it one electron, so it becomes a chloride ion, because it now has one extra electron on the outside filling its outer shell, and then compared to the number of protons in the nucleus. So we've got sodium with plus, chloride minus. Now some of you will look at that and go, hang on, isn't that the compound salt? And you'd be correct, it is salt, table salt, sodium chloride. And it's anionically bonded because it's the attraction of the positive and the negative charges which these ions now have. So this is the sodium ion and that's the chloride ion. Take away the positive, give the electron back to the sodium and take it away from the chloride, you'd be back to a sodium atom and a chloride atom, which are unstable because they have spaces in their final electron shell. So these are ionic bonds, where one species donates an electron to one of the group 7 species, usually chloride, in biological systems. So you can have sodium chloride, you can have potassium chloride, etc. Now the group 2s can do the same thing, they can get rid of 2 electrons. But when a group 2 species does it, such as magnesium, well, it can give away 2 electrons. Now the chlorine can only take one of those electrons, so one chlorine atom will pick up one electron and become an ion, and then a second chlorine atom will pick up that electron and become negative, and that will make magnesium become 2+, because it's got rid of 2 electrons. So it's now got 2 overall positive charges more in the centre than it does on negative on the outside. So to write that properly, you would have MgCl2, because it takes 2 chlorides to take the electrons from one magnesium. The same would be true for beryllium, and the same would be true for calcium, etc. So remember, that's 2+ there, and that's 1- sitting, well, 2- because there's 2 of them. But it's MgCl2, whereas sodium and chloride is a 1-to-1 ratio. In magnesium to chloride, it's a 1-to-2 ratio. And remember that the ionic bond, the ionic because it's 2 ions now which are interacting with each other. It's a weak bond because it's simply a magnetic charge. And that's the only attraction they have. So again, it's easily broken. It's easily separated, so they're going to become their separate ions. So that's essentially ionic bonding. Now, I'm going to stop there so you can think about that. And in the next talk, I'm going to come back and talk about another type of bonding called covalent bonding, and that will get us through the bonding section of this serum. So thank you for listening, and obviously ask me any questions that you have regarding what I've said there.